I'm Sara.
And I'm Sean. Today we're talking more chaos and recursion with the founder of Desmos, Eli.
So this one, we're going to switch over to the geometry tool. And one of the things that we like to do anytime we're building something in the calculator is to make it kind of like as general purpose as possible and to plug into other parts of our system. And so, for example, this recursion takes numbers and returns numbers. You can write recursive functions that take lists and return lists. And so you can use that to implement like sorting algorithms, that kind of thing. But what we're going to do for this is take in a point and return a point in the geometry tool. I'm going to start by plotting 3 points on here, and then I'm going to select these. Let's label them, turn on the label. So we've got our A, B, and C. I'm going to put these in a list for a reason that we will see. So I type brackets, and then I can just click on these 3 points. And now I've got a list of 3 points. And then what I want to do is define a recursion that starts with one of these points. And so I'm going to say that initially we start with this point here, A. Pro tip is that the way that I was able to add the reference to A was by shift clicking. Yeah, if you are anywhere inside of an expression and you hold down shift, then you can click on any geometric object to get a reference to that object inside of the list. And then this one is going to use a method where we're going to randomly recurse, where each step we're going to take a midpoint halfway step towards one of the other points. Here I'm going to take my midpoint tool, and let's do this manually a couple times. So I started with A, and then I don't know, one of you pick between B and C of where I should go to randomly next.
B.
Good choice. All right, and then pick another one. I'm going to now take that new point and randomly between A, B, and C.
C.
All right, and then again.
A.
And again.
A.
Ooh, now we're dealing with some randomness. Real randomness is way less random than it seems like it's going to be. All right, and so then the question is, like, let's do this 10,000 more times, and I hope folks don't have anywhere to go for this episode. But we can do this recursively, and so I'm going to write that as a recursive relationship. I'm going to say the nth point is equal to the midpoint of the previous one, f of n minus 1, and a random element of this list. And to do that, I can just do random element of the list, like so. So I've now written a recursion where it starts with this point A, and then like the second point, f of 2, is going to be the midpoint of f of 1, which is A, and a random element of this list of 3 points. Let's see what this one turns out. So if I do f of 2, it looks like it jumped randomly towards C, and f of 3 back towards A, f of 4. So here's where you can see it's like kind of avoiding B a whole lot, right?
It is.
F of 5.
Forever.
Still.
Wait, now I'm questioning whether or not.
There it is.
Okay.
Yeah, people's intuition for randomness is so bad, including mine. All right, and we're going to do the same trick that we just did, where I want to plot the first 10 points, and I can do that by just doing f of 1 through 10, like so, or the first 100 points, or the first 1,000 points, and suddenly you see a pattern emerge. Is this one that either of you predicted?
Well, I mean, it's hard to say I predicted it. I've seen it before.
Okay. So yeah, this here is going to be the Sierpinski triangle, and we can see it fill in pretty deeply. And the fact that this emerges from a random process is wild. But the thing that's so fun about doing this kind of thing in Desmos is that now we can play around with like all sorts of different parameters here. So for example, every time that you've seen this, maybe you've seen the points on an equilateral triangle. But what if it's not equilateral? So we can just try that. We can drag this point and we see that you can get these kind of like skewed Sierpinski triangles. Or what if it was 4 points instead of 3? But the thing that I want to do here is, what if instead of jumping halfway between the previous point and where you started, we jumped some other amount between it? Have you seen that one?
No.
Okay, here we go. I'm going to make this a little bit fewer just so that it runs a little bit faster. And also, I don't like the color red. We're going purple for this. Okay, so how do we write that? Midpoint is going to be half of the weight is in the previous point and half of the weight is in the new random point. And so I'm going to make a new slider. I'm going to set it to half, and I'm going to have it go from 0 to 1, like so. And I'm going to write this manually. So instead of a midpoint, I'm going to take the previous point and give it a weight of A, and the new point and give it a weight of 1 minus A. And so now when it's a half, this is going to be exactly what we just saw. But what if I make A bigger? So now it's going to be weighted more towards the previous point and less towards the random point. Do you have a prediction in your head of what's going to happen as I adjust this?
I have no idea. Maybe it's not going to be so pointy.
Not going to be so pointy. I love that. Let's try it. So what happens is that the triangles start to blend together. and you end up with a path towards the middle. So it's going to end up just kind of converging into this central value. Okay. What if I go the other way? What if I put more weight into the endpoints?
I feel like they're going to spread out towards each endpoint.
Yeah, exactly. You get something that looks like this.
Whoa.
Okay. Should we kick it up one more notch?
Yes.
Yeah.
So this is what happens if you have 3 points. What I want to do is play around with like regular polygons that have a different number of points. And so for this, I'm gonna probably get this wrong. So I'm gonna start by just, let's say like our number of points is 3, and let's say we can go from 3 to like 8 by ones. And what I want to do is eventually I'm going to delete A, B, and C, but I want to graph these kind of on the outside of a polygon. And so I'm going to do cosine of 360 over n times 1 through n, and sine of this. Let's see if this is going to work. So hopefully this is going to give me points on a regular polygon like so. Okay,
Great.
awesome.
Love it.
That worked, and we can try if it's 5 or if it's 6 like this. All right, and now what I can do is have this be my L instead of what I had before. Okay, so we have that. I don't need A anymore. F of 1 is now busted because it didn't know what it was. So I'm going to just say F of 1 is equal to the first value of L. And everything else should be working as it was. Let's start with a triangle again. And I turn this back on, and indeed we get a triangle still. But now what's going to happen if we make it a 4-sided polygon? This was an enormous surprise to me.
What if you change the ratio? Maybe
Let's change the ratio.
Oh, look at that. Much better. I don't know.
So yeah, here we can see we do get that fractal behavior, but not when it's at a half. I think the most fun one of these are actually when we get a little bit bigger. So like if we do 6, it looks wild, but there's a correct ratio here where you get a different kind of beautiful fractal.
Oh, that's pretty cool.
I like that.
And yeah, I think for each one of these, there's like some kind of, it seems like platonic ideal number for having it make a beautiful fractal. And I actually don't know what that number is for the different ones, but for triangle, it must be a half.
Yeah, I think for a hexagon, it's going to be 1 over the square root of 3.7.
That seems right. Simplest form. Amazing. All right, so that is order from chaos.
We had such a good time with Eli that we have even more coming. We'll see you next time for part 3.
With Sara and Sean.